So in this video, we're going to see exercise 1.2 from chapter number 1, number systems. So let's see what are the questions here. So let's go with question number 1. State whether the following statements are true or false. State whether the following statements are true or false. Justify your answers. So statement number 1, we have every irrational number is a real number. State whether this statement is true or false. So very clearly, this is the very definition of real numbers. So actually, this statement is true. Okay, and the way we justify this is we have seen what is the definition of a real number. So real numbers are nothing but all the rational numbers that exist on the number line plus all the irrational numbers that exist on the number line. So as we have seen that when we take any number line, let's take a number line here. So as we have seen, when we take a number line, okay, and on this number line when we draw numbers, so let's say this is 0, this is 1, this is 2, this is 3, okay, and so on. Here we have -1, here we have -2. So we have seen that on a number line these numbers are our rational numbers. Okay, these numbers are rational numbers, but we saw that there are certain numbers which cannot be expressed as a rational number, which cannot be expressed in the form of p divided by q. Okay, and the numbers which cannot be expressed in the form of p by q are called as irrational numbers. And the example of irrational numbers is under root of 2, under root of 3. Okay, so irrational numbers are those numbers which in their decimal form, for example 1.41. So 1.41 is a rational number because it can be expressed in the form of 141 divided by 100. Okay, so this becomes of the form p by q. So 1.41 is a rational number. However, if I consider a number something like 1.412136879358 dot. So in this number you see the number of digits after the decimal point, these all digits are infinite, they do not stop. So this number, a number of this way, a number of this format can never be expressed in the form of p by q like this. It can never be expressed in the form of p by q. Hence it is called as irrational number. So root 2 is one example of irrational number, root 3 is another example of irrational number. So all these numbers, irrational numbers plus rational numbers, are together called as real numbers. That's the very definition of real numbers. And the question or the statement that they have asked is every irrational number, so every irrational number is a real number, This is true because that is the very definition of real numbers. So third, statement number 1 is true. Now let's go to statement number 2. Okay, so here comes statement number 2. Okay, so let's read it. Every point on the number line is of the form under root of m, where m is a natural number. So every point on a number line, which means it can be a rational number or it can be an irrational number, is of the form under root of m, where m is a natural number. So we have to find whether this is true or false. So first of all, let's clear this unnecessary. Okay, so that we can focus on this. Okay, and the question says that every point on the number line is of the form root m. So let's assume this statement is true and let's see if it holds for every number on this number line. Okay, so let's assume that this is true, that every point on number line can be expressed in the form of root m, and let's see if that is really possible. So I'm going to start with 0. So 0 can be written as under root of 0. So yes, this is true. 1 can be written as under root of 1. Square root of 1 is 1. So this is true. 2 can be expressed as under root of 4. So yes, our statement seems to be true, that every point on the number line is of the form root m. Okay. 3 will be under root of 9. Square root of 9 is 3. So that is also true. However, let's go a little bit deeper and let's consider this number in the middle, which is 1.5. Okay, 1.5. So 1.5 is also a number on a number line because they have said every point on the number line should be of the form root m. So consider this point now, 1.5, which is at the center of 1 and 2. Now 1.5, let us try to express 1.5 in the form of root of something m. What will be that number m whose square root will be 1.5? Now what I'm going to do is I'm going to square both the sides of my equation. Square both the sides of the equation. So this is going to be 1.5 square as equal to m. So 1.5 square is 2.25 as equal to m. So m becomes equal to 2.25. However, let's read the question again. Okay, let's read the question again. They have said that every point of the number line is of the form root m, where m is a natural number. Is m a natural number here? No. 2.25 is not a natural number. In fact, it's a rational number. So m is, so we have found a point on number line 1.5, which can be written as a form of under root of m, but that m is not a natural number, it's a rational number. So thus every point cannot be of this form. Some points 1, 2, 3 are there, but not every point. So this statement also becomes false. Okay, let's go to statement number 3. Okay, where is statement number 3? Yes, statement number 3 reads, zoom in. Statement number 3 reads, every real number is an irrational number. So every, again let's go to the definition. Every real number is an irrational number? False. Real numbers can be either rational or irrational. Every real number cannot be a rational number, and every real number is not an irrational number. In fact, these two sets are not common to each other. So if you remember the diagrammatic representation that we had done, okay, let's do it again. So this is my box of, we say, rational numbers. This is my box of rational numbers, and there will be a separate box of irrational numbers. There is a separate box of irrational numbers, because the very definition of irrational numbers are numbers which are not rational. So this is my box of irrational numbers, and together these two make my real numbers. So together they form a bigger set called as real numbers. So now the question reads that every real number is an irrational number. So is every real number an irrational number? No. Some real numbers are rational numbers and some are irrational. So again, this is basically testing the definition of real numbers. If you know the definition of real numbers, you can very easily conclude that this statement is false. So I'm going to mark here false. So this completes our question number 1 from exercise 1. Now let's go to question number 2. Question number 2 reads, yes. Now, question number 2 reads, are the square roots of all positive integers irrational? Now, this is the question that is being asked. It's like a yes or no question. Are the square roots of all positive integers irrational? If not, give an example of the square root of a number that is a rational number. Now, again, this is a very straightforward question. We have, okay, let me clear out some unnecessary information. Yes. So here itself we have seen that square root. So these are all square roots. So are the square roots of all positive integers irrational? No. Square root of all positive integers are irrational? No. Square root of some positive integer. So 4 is a positive integer. Square root of 4 is not an irrational number. It's a rational number. 2. Okay. Let me in fact extend this number line here. Okay. And we have this 4 here. Okay. Now if I want, so square root of positive integer, so this is a positive integer 4. If I take a square root of 4, I am getting 2. So is 2 a irrational number? No, it's a rational number which can be expressed in the form of p by q. So are the square roots of all positive integers irrational? False. Or it's not true, or it's not true or false question, it's a yes or no question. So no. And if not, give an example of a square root of a number that is rational number. So example is 4. So I'm going to write here example square root of 4 is equal to 2, which can be written as 2 by 1, which is of the form p by q. Okay, and thus this becomes our rational number. Okay, square root of all positive numbers is not irrational. Square root of some positive numbers or positive integers is irrational. For example, root 2, root 3. But when we go to root 4, it is equal to 2, which is a rational number.